Professor, did you get my email?
Oh, about the resubmitting the assignment? Yes, I did.
Yeah, I didn't see your email last night. I just saw it today when I sent you my first one. I'm sorry for sending you two, by the way. I didn't see.
That's okay. So you've submitted it by now?
I couldn't redo it on Blackboard. I mean, I sent it to you as a PDF, just to show you that I had it done, but because I had accidentally submitted something once on
Okay.
Blackboard.
I will send you another email later. I would like it submitted on Black. Wait. Oh, shoot, you're right. I set the settings for the first assignments to allow for unlimited submissions, but I completely forgot to set the same settings for the second assignment.
Oh, okay, okay. When you said resubmitted, I was looking to see if I could do it. I sent you a copy
Right.
just to show you I had it done, but I can resubmit it through Blackboard if you like to switch up the
Yeah,
settings.
do that about half an hour after this lecture ends.
Okay, thank you.
Okay, I totally forgot that resubmissions don't work on this assignment. That was not intended. That was me forgetting.
Okay, thank you so much.
No worries. Okay, let's get started. First off, are there any questions? So I would like to remind everyone of the important fact that there will be, so a reminder, midterm on Monday to Tuesday. Monday noon until Tuesday noon. And I'll probably send the questions by email or post them online. And then they will be submitted on Blackboard. It's going to be similar to a regular assignments. So same submission instructions as the assignment. Right. Now, I'd like to start off, unless there are any questions, with one of the integrals that I wanted to do last time during trig day. So one leftover integral from trig day. And that's the integral of the square root of x over 1 minus x dx. And this is going to be done with a trig substitution, but the problem is that this isn't directly in the form of Pythagoras. There is no 1 minus x squared. But there is an x, and there is a 1 minus x. So there's a pretty big brain substitution that can be made at this point. Can anyone guess what it is?
Is it one of the arcs or?
Well, there's no identities that apply. We want an identity to apply once we put this in. So if I replace X with something, I'd like some identity to hold, trig identity to hold.
Not log, right?
No, it's going to be a trig function.
Oh, okay.
Is it the let u equals 10 u over 2?
That's a substitution most generally. Where you use that substitution is where you have a function that's a rational expression of trigonometric functions. And that turns trigonometric functions into rational functions. At this stage, we do not have trig functions, so that's not the substitution to use.
Okay.
So I'll tell you what the answer is. It's not x squared. If it was x squared, then you substitute u is sine x. But you can do the next best thing and substitute sine squared x. Then what is du?
I'm sorry, can you explain that one more time?
Well, we're going to see, well, 1 minus sine squared is cosine squared x, right?
Yeah.
So this 1 minus x becomes a square, and x also becomes a square because it's just sine squared. So that gets rid of the square root. So the problem is we can't take the square root of this expression. But what if we make this substitution? Then suddenly we can get rid of the square root, as we're going to see in a moment after the substitution is performed. But the general intuition is if you had 1 minus x squared, then you'd let u be sine x, right? But here you have 1 minus x, so we let u be sine squared. Does that make sense?
Yeah, and then the rule, so you can't get the squared of what we have now because why again?
Well, you can't rewrite it in any way, right? Our goal is we only have a very small number of actual integrals that we know how to evaluate, right? There are 11 basic integrals. And everything involves getting something in terms of those functions. Well, this isn't in terms of those functions, and there's now no reduction formula to apply to it. So we're stuck, right? Like you can't solve this integral by inspection. Do you agree?
Yeah.
And what are you going to do? You can't partial fractions it. It's a square root partial fraction, so get rid of square roots. It's not a rational function. So you have to do some substitution. There's so now why would you think to do a trig substitution? Well, you probably wouldn't. This is a very clever trick. If you have enough experience, you might think of this. But if you had 1 minus x squared, then it would really be suggesting a trig substitution, right? Because last time we saw a bunch of examples where we had the square root of 1 minus x squared. And there we always substituted sine x, right? Well, here instead of this, we have the square root of 1 minus x. Okay, so if we set u equal to sine squared x, then what is du equal to?
Would it be 1 over x dx?
Well, that would happen if u were equal to logarithm of x, but u is equal to sine squared x. So we want to take the derivative of sine squared, right? So the derivative of sine squared is not 1 over x. Far from it, right? So we just want to differentiate this function. How do we differentiate this function? This is some calculus stuff.
Do we set up like sine x times sine? Well, I don't know.
Well, okay, which rule do we apply? What rule do we apply at the top level?
Power rule?
Oh, not exactly. Okay, someone PM'd me the answer. So power rule would happen, power rule differentiates x to the n, right? But it's not x to the n, it's a composition. It's a composition x squared composed with sine x, right? That's a bad notation to write, but imagine the function f of x is equal to x squared. Yes, so chain rule. And then the function g of x is equal to sine of x. Then sine squared x is f composed g, right? So for differentiating sine squared x, we use chain rule. So someone on chat, someone on voice, tell me, how do I use chain rule on this?
It'd be f of g of x times g prime of x.
Well, f prime of g of x, well, that's chain rule. So what in this concrete situation with our concrete functions, what is it?
Sine squared of x, or negative sine squared of x cosine of x. Wait,
Why do you have sine squared? What's the derivative of x squared?
sorry, 2x.
So what's 2 what?
2x.
Okay, that's the
Yeah.
derivative of x squared, but what does that mean in terms of this?
2 sine of x.
Times what? Times the derivative of sine x, which is what?
Cos of x?
Yeah. Okay. It is very bad for me if people can't differentiate this. I am in a lot of trouble if people can't differentiate this. Okay, you should know how to differentiate sine squared x. That is a good thing to know. Chain rule, right? So it's the composition of x squared of sine of x. Okay, well, if we do that, then this integral becomes what? How can I rewrite it? Sorry, I made a mistake. I mean to say something else. I mean to say, let's x equal. Is this what was confusing people? Let's x equal sine squared u. So dx is 2 sine u cos u du. Right. What we're doing is we're substituting something for x, not something for x is sine squared u. Right. So I think there might have been some confusion because of that. Right? We're making the expression more complicated to make these trig identities go through. Okay, with this in mind, what does this become?
Square root sine squared u over 2 sine, 1 minus 2 sine u cosine u du.
Well, it's 1 minus x, so it's 1 minus sine squared.
Oh, okay, my apologies. So,
But then we
yeah.
also have something else. What else do we have?
The dx, 2 sine u cosine u du.
Yes. Okay, well, so the integral, that's by Pythagoras, is the square root of sine squared u divided by cosine squared u. I'll take the 2 out front, and then I have sine u cos u. And if I look at this, the square root goes away. I get 1 divided by cosine. So cosine, I have a cosine here, I have a cosine here, they cancel out. And then I have a sine here and a sine here. So I just get 2 times the integral of sine squared. U du. Oh, whoops, I'm doing a homework problem in class. That's bad. Okay, let's do the homework problem in class. What substitution? Sorry, no, it's not a substitution now. Which trig identity do I use?
1 minus cosine squared u.
Yes. So what is that equal to?
The cosine. Wait, what?
Sorry, you said 1 minus cosine
Squared u
squared u. Well,
equals. Sine
you're
squared
missing
u?
a factor of 2, and I think your sign is off. It's 2 cosine squared. U minus 1, right? What is that equal to?
Wait, is that from the Pythagorean identity?
Well, so this is equal to 2u, 2u cosine 2u. Well, on the assignments 3, this is listed at the top, right?
Yeah.
This is the actual formula given there. So I'm not
Oh.
sure. It comes from the Pythagorean identity in terms of the fact that cosine 2u is equal to cosine squared u minus sine squared u. And then using Pythagoras, you get this formula.
Oh, yeah. Okay. Got it.
Right. But we can rearrange this. And so we get that cosine squared of u is equal to 1/2 cos 2u plus 1. Right?
Yeah.
Okay. Well, we have this 2 here. So that goes away. And so we just get the integral of cosine 2u plus 1 du, right? Now, we can do the substitution. Do we want to do a substitution? Okay, we can be rigorous if necessary. Or we can choose to not be rigorous. Let's do it by inspection. By inspection, what's the antiderivative of this?
Negative sign.
Well, the derivative of sine is cosine, so it's not negative.
Sine.
But is there a prefactor? So let's say
U.
it's sine 2u. What's the derivative of sine 2u? With respect to u. This is again a chain rule question. Sine 2, let's say sine 2u du of this is equal to what?
Is there a 2 in front of 2?
Yes, there is. Because chain rule, we multiply by the derivative of the function on the inside. Right? So the antiderivative of cosine 2u is not sine 2u, it's 1/2 sine 2u, right? And then plus u plus c. Okay. Sorry, I made a mistake. This is what cosine squared is equal to. I do not want cosine squared, I want sine squared. Oh, I should mention one thing. I woke up at 5 a.m. today to watch the solar eclipse, and I wasn't able to go to sleep after that. So any errors in this lecture are caused by solar eclipse watching at 5 a.m. Did anyone else watch the solar eclipse?
I didn't even know it was happening. So no.
I didn't either.
So- It depends on where you were. Most regions of the United States did not have very good coverage, but I'm in Ontario, Canada. So where I was, there was 80% coverage. The sun rose in an eclipsed state. It was pretty cool, but the 2017 eclipse was also pretty cool. I think that one was a bit cooler. Okay, so the actual identity that I want to use is that, sorry, I used the wrong identity. I want to use the identity, let me erase this. That's 1 minus 2 sine squared u is equal to cosine 2u. So sine squared of u is equal to 1/2 1 minus cosine 2u. Right? And this is one of the homework problems, by the way. So 1 minus cosine 2u. And then that becomes u minus 1/2 sine 2u, which we just discussed, plus c, right? Now, let's say I substitute back. Well, the thing is that I do not know what sine 2u is. I know that sine of u is square root of x, so I should expand sine 2u. How do I write sine 2u in terms of x? So instead of this, I will write this as sine 2u becomes 2 sine u cos u. Plus c, right? Now, what does u equal to? If x is equal to sine squared u, what does u equal?
Is it 2u or just u? Or
Well, x is sine squared u, so what is u equal to, right? We made the substitution. Where do you mean is it 2u?
is it
Where
arc?
would it?
Is it arc sine?
Yes, arc sine of what?
Arc sine of u? No, sorry, arc sine of x.
Arc sine of what? It's not x because there's a square.
Is it 2?
How do we solve this equation? If x is sine squared u, then the square root of x is equal to sine of u, right? So u is arc sine of the square root of x. Now, what about so sine of u, on the other hand, is equal to square root of x. And here we have sine of u. What about cosine of u? How can we write cosine in terms of sine?
One minus sine squared u.
Yes, except for the fact
Oh.
that we have to put that all in the square root, right?
Right.
And then sine of u is equal to square root of x. And so cosine of u is equal to the square root of 1 minus sine squared u, which is the square root of x squared, right? And so cosine of u is equal to 1 minus x, the square root of 1 minus x. So all of this becomes arc sine of the square root of u, sorry, the square root of x, minus root x times the square root of 1 minus x plus c. So this problem is interesting in what we had to do at the end in order to rewrite everything in terms of x. Any questions about that?
So once we get our answer in terms of u, we set our x's and u's so that we rewrite it in terms of x.
Yes, so we definitely have to rewrite it in terms of x because the original question is in terms of x, and u is just something that we introduce in the middle of our work. As a final answer, it's meaningless, right? If I wrote this equals this, then it makes sense without context. If I wrote this equals this, then it doesn't make sense unless you know what my u was. So that doesn't completely answer the question, right? But this is a complete answer to the question. It's an antiderivative in terms of x, which is the original variable set out in the problem. So when we have u, it's easy to solve for that. Now we could also drive this equation in a different way. We could also write u is equal to arc sine of the square root of x, and then we could consider cosine of arc sine of the square root of x. So here's a second approach to the problem. Then we could write a triangle, and we're going to see that this is 1 minus x, square root of 1 minus x. So we'd like to set up a triangle such that the cosine of this angle is equal to square root of x. So cosine is the adjacent divided by the hypotenuse. So what should I set the adjacent side to?
Root x.
Yep. And the hypotenuse too?
1.
Okay. And so what does this side become?
So 1 minus x squared.
1 minus the square root of x squared. So 1 minus x.
Oh, okay.
And all square rooted, right? And then sorry, this is arc sine. I did it backwards. Okay, eclipse. This is what happens. We want the sine of the angle to be square root x. So I should actually draw it like this. Okay, the eclipse, the waking up at 5 a.m. is really getting to me. Now we'd like to take the cosine, so that's the adjacent divided by hypotenuse, so that becomes square root 1 minus x. So there are two ways that we could have derived this answer. We could have derived this answer this way, or we could have written cosine in terms of sine u, and then derive the answer in the second way. So those are two ways of doing the back substitution. This method you learned last time, so it's more of a robust method. This method involves a bit of a trick.
So after we write the answer in terms of x, what part of the problem was asking for, like?
Well, the goal is to find an antiderivative of this function, right? So here we've written some function. It's a function of x, and its derivative is this. So we're done, right? We solved the integral, gave a function.
Yeah.
The indefinite integration problem is solved. So the problem was just to integrate this. And the main idea was that you could do this clever substitution. And then that works. Okay, so that's one leftover exercise from trig day. Let's move on to the material of this lecture.
Sorry. So we got our answer, and then the triangle part was just.
So I showed you that when you did this cosine u is equal to square root 1 minus x this way, you could do it in a different way, right? Because you had cosine u, you know that u is equal to arc sine of the square root of x. So cosine u is equal to cosine of the arc sine of the square root of x.
Got it.
So yeah, two methods for finding what cos u is. Any other questions? Okay, let's move on to definite integrals. So we, at the beginning of the course, definite integrals. Remember that these are integrals of the form, these are actual area computation problems. These are problems of the form. Integrals with bounds, integral from a to b of f of x dx. And of course, we know how to solve them in terms of an antiderivative, but so you could, these can be solved with indefinite integrals. So these can be solved by finding f of x is equal to the indefinite integral of f of x dx, and computing f of b minus f of a, which is what FTC 1 says. But there is a second way to do those integrals where you keep the bounds in while you're doing the integral. You can also keep the bounds in. And now I'm going to explain how you do that. So first off, for substitution. What does substitution involve? Substitution says, suppose I have f prime is equal to f, and I consider the integral of f of g of x times g prime of x dx. Well, then this is equal to f of g of x plus c, you can say. So this is a statement about this is a statement about indefinite integrals. But as a corollary, this implies that if I put in bounds from a to b of f of g of x times g prime of x, then what is that equal to?
It would be, you just plug in the b and then in terms of
Right, so I would get f of what?
b or
Not b.
g of b
Yep.
times g prime of b.
No, not times g prime of b. We just plug in, this is the antiderivative, so you plug in the value.
Oh, right, okay, and then minus f of g of a.
Yeah. And then we forget about the plus c because you get plus c here minus c here, so the c's cancel. But notice f prime is equal to f means that the antiderivative of f of x dx is equal to capital F, right? So f of g of b minus f of g of a can also be written as the integral from g of b, sorry, from g of a to g of b of f of x dx. So what we obtain is substitution for definite integrals. And what this says is that the integral from a to b of f of g of x times g prime of x dx is equal to the integral from g of a to g of b of f of x dx. So the bounds change, and what happens when the bounds change is that we no longer have to substitute back for u. So instead of substituting back for u, this is already in terms of x, this is already a number. There's no back substitution for x. When you compute the right-hand side, you get a number. So there is no writing things in terms of x. No step of replacing u with x. And I'll give you an example of this. But first, are there any questions? I think the example will illustrate it. So suppose that we have the integral from 0 to pi over 4 of tan x secant squared x. Dx. So there's a substitution that's crying to be made. What is that substitution?
Secant x tan of x?
Well, the derivative of that is going to be complicated, right?
Yeah.
There's some trig function whose derivative is part of this expression. This is one of the more straightforward substitution problems. No clever tricks required.
Is it just tangent?
Yeah. U equals tan x. And then what is du equal to?
Secant squared x?
Yeah, exactly. So with the substitution, what does the integral become? Let's leave the bounds for a second. What does the body of the integral become?
U du.
U du, right? Now, what do the bounds become? So if the bounds transform as g of a to g of b, so the bounds become tan of 0 and tan of pi over 4. Can we rewrite what those bounds are? What is tan of 0?
0.
Yep. And now remember that pi over 4 is equal to 45 degrees, right? And that's tangent is the ratio of sine to cosine. So what is the ratio of the sides of the triangle of the 45-degree angle triangle?
Is it 1/2 and then √3/2?
No,
Or,
it's a
no,
45 degree.
√2/2
It's
and then
no, if so well, those are what the sides are. What is the ratio of sine to cosine?
Is it
So
just
this is
one?
sine pi over 4. This is cosine pi over 4. What is the ratio?
Is it radical 2/2 over radical 2/2?
That is also known as
1.
1. Yeah. So at the 45-degree triangle, there's a symmetry, right? It's so yes, it's sine is equal to √2/2. But in particular, cosine is also √2/2. So it's just 1. So we can rewrite this as the integral from 0 to 1 of u du. And then that becomes u squared over 2, right? And then we evaluate the bounds from 0 to 1. So notice, we are not substituting back for u is equal to tan. We are directly evaluating the bounds here, and it'll give us a number. And what number is that? So if I plug in 1, I get 1/2, right? Minus 0. So that's 1/2. So if I want to work in the world of definite integrals, I don't have to do this substituting back and writing things in terms of x if I transform my bounds correctly. But the key is that you have to remember to transform the bounds.
I'm sorry, I just have a quick question.
Yep.
Why did you write u squared over 2? Where did that come from?
Because it's the integral of u du. What is the antiderivative of
Oh.
just x, right?
Okay. All right. Thank you.
So yeah, this is a pretty classic example. The key is that usually we would solve this by then writing tan squared over 2. But instead of writing tan squared over 2, you could transform the bounds and just evaluate the bounds in terms of u. And then there is no substituting back step. Let's do another example. Right, here's a good one. Let's say I do the integral from 0 to pi over 6 of cosine to the 5th 3x dx. So let's do, we're going to do 2 substitutions. What's the first substitution that we'll make? And this is also relevant for the homework, by the way. This will tell you a hint for problem 2 on the homework. Let's first get rid of this 3x. How do I get rid of the 3x? I let u equal
Uh, 3x.
Yep. Then du is equal to 3dx, right? So what does this integral become? First off, what do the bounds become? Let's start with that. The bounds are what?
1,
1,
or
why 1?
is it cosine of 0?
Look at the substitution that we're making. Right? We're evaluating the function 3x at 0 and 3x at pi over 6. So if we're making a substitution, basically what this says is that, let's rewrite this. If you have this, then you're making the substitution u equals g of x. So let me rewrite that. Here, I can do a somewhat clever way. Here we are. So another way to write this is if I have the integral from a to b of f of g of x times g prime of x dx, then what I do is I make a substitution. I let u equal what? This is literally the most general substitution possible, in the situation of substitution possible. What are we substituting? Let u equal what?
G of x?
G of x. Then du is g prime of x dx. And so this integral becomes the integral of f of u du, right? And now if I put bounds, the bounds become g of a and g of b. The fact that I wrote x before, it doesn't matter because this is just a number. This number is the same as this number. It doesn't matter if the variable is u or the variable is x. In the end, it becomes a single number, right? These expressions define numbers. They're equal. So then how do the bounds transform? The bounds transform as the function that I've substituted. So going back to this example, by the way, does that make sense? Any questions about that? So going back to this example, I wanted to deal with this example by dealing with the 3x. And I'm going to deal with it once, then forget about the fact that there was ever a 3. I won't have to substitute back. I can forget about it entirely. So how do the bounds change? What do the bounds become? The bounds were originally 0 and pi over 6. What does 0 become? When I apply this function.
Would it be 3 times 0, so 0?
Yep. And what about the pi over 6?
3 pi over, no, 1 pi over 2.
Pi over 2. Good. Right. So now we get cosine to the 5th of u du except what am I missing? I need to put a prefactor. What is the prefactor? So dx is 1/3 du, right? We shouldn't forget about that. Okay, now here's the beauty of working with bounds. I can forget that I ever made the substitution. Now I'm just solving an integral in terms of u, and eventually I'll just plug in these bounds. I can completely forget that I ever made the substitution. Okay, let's continue. So when I have an integral like this, what you actually do is you rewrite everything in terms of one trigonometric function. You can rewrite this as, well, cosine to the fourth of u times cosine of u du, which is equal to so again, this is a big hint for the homework. 1 minus sine squared u squared. So I can write, I can more informatively write cosine to the fourth of u as cosine squared u squared. Right? And now there's a substitution that's screaming to be made. What's the substitution that I let w equal what?
One minus sine squared u.
The derivative is going to have 2 sine u cos u, and that's too complicated of an expression to factor out of this, right? What's easy to factor out of this? This is easy to factor out of this, right? What is this the derivative of?
Of sine.
Yeah. W is sine u, then dw is equal to cosine of u du. And that's great. So this becomes 1/3. Then I get the integral. Now, how do the bounds change? What is a sine of 0?
1.
Cosine of 0 is 1. Sine of 0 is 0. So you should always keep the graphs in mind. It's always good to keep the graphs in mind. This is sine. This is cosine. Right? And this point right here, this point right here, that's pi over 2. And what is a sine of pi over 2?
1.
Yeah. So the bounds change to 0 to 1. Now, what does the integrand become? 1 minus sine squared. What does sine squared u become? In terms of w.
W squared.
Yep, 1 minus w squared, and then cos u du is dw. And now I can forget that I ever made the substitution. All I'm going to do is I'm going to integrate this and find the bounds. Now, okay, I just expand this. So I get 1 minus 2w squared plus w to the fourth dw, right? And what's the antiderivative of this? 1/3 times what? Do the inspection.
Is it just, does it equal 0? I mean, 1/3.
We just want to write the antiderivative at the moment.
Oh, okay. So in terms of w.
Yep.
W. 2/3 w
Yep.
to the third
Plus what?
plus W to the 5th over 5.
Yeah. 1/5 W to the 5th. Okay, now this is a definite integral, so we put in the bounds. I draw this horizontal line, which means I'm evaluating it between these 2 points. So that becomes 1/3. Then if I just plug in W equals 1, that's pretty easy. I get 1 minus 2/3 plus 1/5, right? And then I get minus, and then if I plug in W equals 0 here, I just get 0, right? So let's do the algebra. I get 1/3. Then I can write this as 1. Then I want to combine these to a common denominator, so I cross multiply. I get 10 over 15 plus 3 over 15. And then I may as well write the 1 as 15 over 15. So if I subtract 10 from 15, I get 5, and then I add 3, I get 8. So I get 8 over 15. 15 times 3 is 45. And that completes the question. Now, so in fact, integrating with bounds is easier than integrating without bounds, because you can forget that you ever made the substitutions, and you never have to do the substituting back step. So remember how in this problem that we had here, we had to substitute back, and this was tricky? Well, if this were a definite integral, then you would no longer have to do that, because you just plug in the new bounds, right? So this is a pretty clever thing. It makes a lot of problems easier if you have bounds. Okay, so I've explained how to handle substitution. What about parts? Well, parts is actually handled pretty simply. I'll just give you the formula. The integral from a to b of f prime of x times g of x dx is equal to f of x times g of x. And then I evaluate it at bounds. What are the bounds? Should the bounds change? Is there any reason for the bounds to change?
Nope.
Yeah, there's no function to transform them by. And then minus the integral of f from same bounds again. F of x times g prime of x. Right? So the bounds don't change, and the cross term is evaluated at the 2 different bound positions. Let's do an example. So let's say I do the integral from 1 to e of x log x. So I'm going to integrate this by parts. Which function do I want to differentiate, and which function do I want to integrate?
You want to differentiate the x?
But then you're
Or-
going to have to integrate the log, and log is hard to integrate.
Okay, okay.
So we're differentiating the log, right? So let u equal log x. And then dv is equal to what? Sorry, I wrote that wrong. We're differentiating yeah, no, that's right. X dx. So if it were something like e to the x, you'd like to differentiate the x. But in this case, we're actually going to integrate the x. So it's going to become an x squared. So it's a bit counterintuitive. But the reason that we're doing it is because we really don't want to integrate the log. We prefer to differentiate the log. So du becomes 1 over x dx. And what does v become?
1 over 2x squared.
Yep. So if we have these, then the cross term is x log x. I prefer to write it like this: x squared over 2 log x. And then this is evaluated between the bounds 1 to e. Now, here's the beauty of it. We integrated the x, but the log x just became a 1 over x. So if we look at this integral, it's the integral from 1 to e of what?
The x squared over 2 times 1 over x.
So that's just x over 2, right? Okay, I would prefer to evaluate the bounds at the end, so I'm just going to leave this expression here. I'll do everything at the end. And this is easy to integrate. What's the antiderivative of x squared over 2? Sorry, of x over 2.
X squared over 4.
Yep. And then I put the bounds again. So just to be clear, I'm subtracting this. Okay, well, now let's do it. Log of, what is log of e and what is log of 1?
Log of e is e, right? Log of e is
Not e.
1.
It's 1. And log of 1 is?
E. No. 0.
Yeah. What does your graph of logarithm look like? It looks like this, right? So here is 0. Sorry, here is 1. That is obviously not 0. Here is e. And at e, it's 1. Yeah. So important log facts, some important log facts. Why is this, by the way? Because e to the log e is equal to e, right? E to the log a is equal to a. That's the definition of logarithm, right? So log e is equal to e to the 1, right? And what about log 1? 1 is equal to e to the log 1 is equal to e to which power? E to what power is 1?
0.
0.
Yeah. So if you wonder why these identities are true, you go back to the definition of the logarithm. This formula right here is essentially the definition of logarithm. And it's the inverse function of the exponential. And so then you know that e to the log e is e. So what does log e have to be? It's 1. E to the log 1 is 1. So what does log 1 have to be? It has to be 0, right? So, okay, I get e squared over 2 log x, which is 1, minus then log of 1 is equal to 0. And this is all minus e squared over 4 minus 1/4, right? What's e squared over 2 minus e squared over 4?
E squared over 4.
Yep. Minus 1/4. Or to write it more aesthetically, 1/4 e squared minus 1. So here is an example of integration by parts where we just kept the bounds in. It doesn't make integration by parts any easier. It does make substitution easier, though. but sometimes you use substitution and parts together. And then the appeal basically is that here there were never any indefinite integrals. You weren't ever asked to find the antiderivative of something. You were asked to find a definite integral. You were asked to compute a number. So this process stays entirely within the world of definite integrals. There are no integrals without bounds. You start with an integral with bounds, and at every stage in the middle, you have an integral with bounds. And then you now know how to deal with bounds. All of the rest of the tricks that we did, they were just methods for using substitution, right? Or methods for doing algebra, like partial fractions, which doesn't even involve substitution. Well, the bounds just don't change. You're just doing algebra. You're just rewriting the expression. The only actual integration techniques that we have are inspection. Well, inspection, you just write down the answer. Or then parts and substitution. And I've told you how the bounds change in parts and substitution. Well, in particular, they don't change for parts, and they change as with the function that you're substituting for substitution. So substitution with bounds is good. It's easier than doing indefinite substitution because, as we saw before, this step of rewriting everything in terms of x was annoying, and substitution with bounds, you just avoid the step of rewriting everything in terms of x. And it's very easy to change the bounds because you just evaluate the function, right? So substitution with bounds is good. If you have bounds, you should not compute indefinite integrals. You should change the bounds when you substitute, and that makes your life easier. Any questions about that? So I think these two examples are good. This is a bit of a tricky concept because you have to remember to, well, it's not so much tricky as it's easy to forget that you have to change the bounds, right? And you have to be sure to not forget to change the bounds. So this is an excellent example. You started off with 0 to pi over 4. This is a classic substitution example because the secant squared screams as the derivative of tangent, and you just have tangent right here. So you make the substitution. The secant squared x dx becomes absorbed into a du, so you get u du. The bounds transform. Now, typically, if the bounds are going to be here, they're going to be angles for which you can compute the value of tan of, and pi over 4 is definitely an angle that you know the tan of, because it's just 1, because it's the ratio of sine and cosine. And at 45-degree triangle, these two sides are equal. Then this example, it's in general deals with odd powers. The second question on the homework deals with examples like this. They're without bounds. But remember that you were going to do this substitution, and it's going to absorb one of these, and then you're going to have an even power. And you rewrite everything in terms of the thing that you're going to be substituting for. And then that just transforms it into an integral of a polynomial. Now, on the assignment, you have indefinite integrals, so you're going to have to substitute back. But here we have bounds, so we didn't. This doesn't appear on the assignment, as in the bounds changing. I wanted to put some problems, but the assignment was already full. And so I made the choice, it might not have been a good choice to not include any problems which involved changing bounds. Okay, let's move on to the next major topic. Or it's only been an hour. Is it too early for a break? I think that let's take a 15-minute break. Or you know what? Let's do 2 breaks today. Let's take a 10-minute break. Let's break until 7:20. Does that sound good?
Yeah.
Cool. Okay. See you at 7:20. And then if you think of any questions, you can ask them after the break. Okay, let's get started again. Did any questions come up during the break? Has anyone thought of anything to ask about the previous things that we discussed? Okay, let's get started. So before I mentioned that there were two parts of the fundamental theorem of calculus and that we'd only do one, then we do an entire unit on computing integrals, and then we'd return to the second statement. So to recap, what did FTC 1 say? Well, it said that if f prime equals f on AB, and capital F is more generally continuous on AB, which just means that it's continuous at the endpoints, and F is integral, F is integrable. Then what? This is the theorem that lets us compute definite integrals, right? So the theorem says that the integral from a to b of f of x dx is equal to what?
F of B minus F of A.
Exactly. So why is it important? It is important. This is important because it computes definite integrals. So recall how hard it was to compute the integral of x cubed or x squared from Riemann sums. So the problem of integrating from 0 to 1 on a specific interval, the function, let's say x squared, that's the one we did in class. X cubed you did on the homework. X cubed dx, how hard this integral was with Riemann sums. Whereas for how we do it now, it's absolutely easy. But now we can do this integral very simply. What do we write down? We write that this is equal to, so what's the antiderivative?
X cubed over 3.
Yep. Then we put the bounds. Then we get 1/3 minus 0 is equal to 1/3. And done. Bam. Look at how much easier it is. So FTC 1 is absolutely great because you had to suffer through the pain of doing this with Riemann sums on homework 1. And now, bam, done. Just like that. So this establishes the fact that antiderivatives are very important. But then we come to a question. Does this method always work? Is this a robust method? In other words, will an antiderivative always exist? And this is actually a good question. So one thing that we find out is that so first off, it is a result that if a function is differentiable, then it is continuous. But that's a bit of a side remark. That's not a main point right now. Suppose that's f prime, or let's say capital F, suppose that G is equal to f prime. Then what can we say about G? Any guesses? So differentiable function is continuous, right? Now, what about its derivative? What do you think is true of its derivative?
It might or might not be continuous.
You are correct to err on the side of caution. You may guess, you may guess. That's G must be continuous. But this is false. Is not generally true. And the examples are very pathological. So what you can have is you can have a function like sine of 1 over x. If we look at what the graph of sine of 1 over x looks like, what happens is, well, let's first draw the graph of 1 over x. It looks like this, right? Our classic asymptote at 0. So as x gets close to 0, 1 over x hits all big real values, right? Let's imagine that we start at 1, then 1 over x is equal to 1, right? Now let's imagine that we move from 1 to 0. Then 1 over x moves from 1 to infinity. So now what happens to sine 1 over x? Well, let's say that this is 1. Then here we have sine of 1, which is some value. It's, let's say, here. And then what happens is that suddenly it goes through all of the values of sine x. So then it starts moving, and then it starts going quicker and quicker. And then suddenly it starts doing loops very quickly, and then just looks like a solid line. It oscillates very, very quickly in here, and these rate of oscillation is getting infinitely quick. So the function looks absolutely terrible. This function is continuous. It's not continuous at 0. It's not defined at 0, but it is continuous everywhere else. But now you can consider a function like x squared sine 1 over x. And what happens now is you're taking this crazy oscillating behavior, let's say 1 over x squared. And you're also taking the function 1 over x squared. Let's say taking the function x squared. Here I'm drawing x squared and negative x squared. And so you still get that crazy oscillating behavior. But now it's being limited in range to this very small range. So this function is continuous. And you can show that this function is also differentiable. And if you compute what its derivative is, let's just compute what the derivative is. So we do product rule. We get 2x sine 1 over x squared. And we also get x squared. Then we get the derivative of sine is cosine 1 over x squared times 2x. Now this function is continuous at every point except for 0. Does the derivative, okay, so here's the question. Does the derivative make sense at 0? Is this function continuous at 0? Well, yes, it is. It's, sorry, is this function defined at 0? That's a separate question. Does the derivative exist at 0? This function is not continuous at 0. Okay, I'm doing this wrong. Remember how I watched the solar eclipse at 5 a.m.? F prime is defined at 0. But F prime is not continuous at 0. Sorry, the reason is because I've differentiated 1 over x squared wrong. The derivative of 1 over x squared is negative 2 over x cubed, right? So we get negative 2 over x cubed. And here, this is why exactly the point. So f prime, we get a formula for it. That's it's sine of, sorry, 2x sine 1 over x squared. This term is very well behaved as x goes to 0, because sine oscillates between 0 and 1, but 2x goes to 0. But if we look at this term right here, this term is a troublemaker because we get 1 over x cosine 1 over x squared. So this function doesn't look like it's continuous at 0. Now the question is the derivative even defined at 0? Is this function differentiable? And you can show that f prime is differentiable and its derivative is 0. So f prime is defined at 0, but this formula doesn't work for it. You do a separate argument. And so what happens is that it's discontinuous, but it's discontinuous in this crazy oscillating way. Now, what you can show, so it's not true that the derivative of a continuous function has to be continuous. And in general, all of the examples have this crazy oscillating behavior. This is known as an essential singularity. And it's a very weird kind of discontinuity. But there's another kind of discontinuity, and that's the discontinuity that we're actually used to picturing. It's when the function goes right here, it has a gap and it jumps to some other value, right? This is known as a jump discontinuity. And the property of an essential discontinuity is that the function takes on all real values near the discontinuity. Arbitrarily close to discontinuity. This isn't exactly correct, but it is approximately correct. So don't quote me on this because you can square the function and then that wouldn't happen. But the point is that it's really going all over the place, ridiculously close to the value. But in a jump discontinuity, that doesn't happen. And you can actually prove a theorem. There is a theorem that says that if G is equal to F prime, then G has no jump discontinuities. It can have crazy discontinuities like this function, but it can't have a jump discontinuity. But what does that say? Now, remember on homework 1, we considered the function f of x equals 0 for x is less than 1/2, and 1 for x is greater than or equal to 1/2. And this function has a jump discontinuity. Therefore, there does not exist a function sum f with f prime is equal to f. So the fact that this function has a jump discontinuity means that it has no antiderivative. I'm not being rigorous because I'm not even defining what a jump discontinuity is. I'm not defining what an essential discontinuity is. I'm not actually showing you that the derivative of this function is defined at 0. I mean, basically, what does it mean that the derivative is defined at 0? You consider the limits as h goes to 0 of, well, this function is defined at 0. F of 0 is equal to 0, right? It's continuous, it's defined at 0. So you consider the limits as h goes to 0 of h squared sine 1 over h squared divided by h. Oh, well, this is very easy. This is the limits as h goes to 0 of sine 1 over h squared. So sine is oscillating all over the place. Sorry, I have to keep writing limits. Sine goes all over the place, but it only goes between 0 and 1. And h is going to 0. So this limit does exist. It's equal to 0. So that shows that f prime is equal to 0. Good. I've actually completed all of the details. F prime of 0 is equal to 0. While f prime at every other value is given by this formula. So now we see that this function is differentiable at every value, but it's not continuous because this function blows up to infinity. But it's blowing up to infinity not uniformly, it's also going to 0 infinitely often. So this function is blowing up to infinity, but as it's blowing up to infinity, it's jumping between positive and negative infinity. So this is a super crazy behaved function. And this type of singularity is known as an essential singularity. So I've shown here, just using the definition of a derivative, that this function is differentiable at 0. And then we know what its derivative at 0 is. And it's continuous everywhere else, and we can just find a formula for its derivative everywhere else. And it's really clear that this is very badly behaved. So f prime is not continuous at 0. But it is the antiderivative of a continuous function. This function is continuous because as it goes to 0, the values are constrained. So this is a classical example. You would not make this up on your own. It's just one you would make this example up if you were explicitly theoretically trying to construct an example that has a discontinuous derivative and you knew what you were doing. But it's very specifically constructed to have this property. But it can't have a jump discontinuity. And a jump discontinuity is something that looks like this. So remember how we just did calculations for the last several classes? Here we're going to do a bit of a theoretical section, but it's a very hand-waving theoretical section. The point is that this function does not have an antiderivative. But do you know what has an antiderivative? This absolutely insane function has an antiderivative, right? X squared sine 1 over x squared. So you can have functions with essential discontinuities that have antiderivatives. It's a continuous function whose derivative everywhere is this function. This function is defined to be 0 at 0. This is the definition of the function at every other point. And that function has an antiderivative despite being discontinuous. But this function has a jump discontinuity. And so it does not have an antiderivative. But we showed on the homework one, but we know that it's integrable. Or to be more specific, it's integrable on the interval 0, 1. It's also integrable on any other interval. And we showed on the homework that the integral from 0 to 1 of f of x dx is equal to 1/2. So in other words, the strategy of finding an antiderivative does not always work. Of finding an antiderivative and I think that if you're mathematically or scientifically minded, you will be very intrigued by the example that I did before. You can have a function that's differentiable at every point. So continuous functions don't have to be differentiable, but you'd assume that if you have a function that's differentiable, then that would imply some strong properties about its derivative. Well, it implies that there are no jump discontinuities, but it doesn't imply that the function is continuous. And that's really surprising, right? Because
I have a quick question. I'm sorry. Is all of this going to be explained on your notes that you post, or are you able to post this specific note page?
Okay, thank you for reminding me. So I was originally planning on doing typed up notes. I am far too behind on that, so that is obviously not happening, but what can I do? So it occurred to me that I can do one other thing. What's the obvious thing that I can do?
Just post these notes on?
Yes, I am going to post all of the lecture PDFs of everything that I've written up. I'll do that tonight.
Awesome. Thank you so much.
Thanks for reminding me about that. I was going to mention that. Yeah, good. So I will post this. Right now, this is not part of an examinable. This is not part of the examinable material. This is me just motivating fundamental theorem of calculus part 2. And what's the motivation? The motivation is that antiderivatives are important, but do antiderivatives always exist? Does every integrable function have an antiderivative? Well, no. This function right here, it's integrable. We showed that it's integrable on the assignment, but it doesn't have an antiderivative because that is a jump discontinuity. I haven't proven that having an antiderivative implies having no jump discontinuities, but I'm just going to quote that as a result. But when we say that, we can't say that discontinuous functions don't have antiderivatives, because you can have a function that is absolutely insanely discontinuous. It just goes all over the place. It goes to positive and negative infinity at the same time. It just keeps jumping between positive and negative infinity. Well, very large values as it goes to 0. And this absolutely madman function has an antiderivative. But this function right here, defined by this formula, does not have an antiderivative. And it turns out that this type of discontinuity, as far as antiderivatives are concerned, is worse. So that is really surprising. Okay, so the strategy of finding an antiderivative does not always work. There are integrable functions without antiderivatives. So what would you like to know has an antiderivative? So for the sake of sanity, we would like to know that a certain class of functions has antiderivatives. What class of functions is that? So what hypothesis on F should guarantee that F has an antiderivative? Okay, let's go back a bit. I proved that a certain class of functions is integrable. We know that if F is blank, then F is integrable. Fill in the blank.
Differentiable. Continuous.
That is strong enough. It is true that differentiable functions are integrable, but that's also because differentiable functions are what?
Continuous.
Continuous, right? So we know that continuous functions are integrable, right? So we may at least hope that continuous functions have an antiderivative, right? So FTC Part II says that continuous functions have an antiderivative. Now, you may think, well, is this an algorithm for computing the integral of any function? It's a bit of an unsatisfying answer. More specifically, suppose F is continuous on AB. A comma B. Then for any x in this interval, consider capital F of x equals the integral from a to x of f of x dx. So F is because F is continuous on the interval a comma x, this is always defined. F is always defined. We know that continuous functions are integrable, and if it's integrable on the entirety of a, b, then it's also integrable on a to x for any x between a and b. And so we can consider integrating f from a to x. And then the question is, well, how does this function behave? Is this a nice function? Is it a continuous function? Is it a differentiable function? And FTC Part II specifically says, then we know, then the theorem is that dx of f of x is equal to what? Remember what we're trying to establish. We're trying to establish that f has an antiderivative, right? So this should be what should the derivative of this be?
F.
Yeah, f of x. So that is the theorem. This is what this is the theorem. That is what the fundamental theorem of calculus Part II says. Now, of course, this theorem is useless for computing definite integrals because it's in terms of definite integrals. This is theoretically interesting. But useless for computing definite integrals because it's in terms of a definite integral. So fundamental theorem calculus part 1 is the most important theorem in calculus, or at least in calculus B, arguably the mean value theorem, which proves fundamental theorem of calculus part 1 is the most important theorem in calculus. But the most important theorem in calculus B is the fundamental theorem of calculus part 1, because it solves definite integral problems so long as we find an antiderivative. It also establishes that the notion of an antiderivative is an important concept to consider. This theorem is a theoretical reassurance that antiderivatives exist for continuous functions. But there's another way that this theorem is often said. This theorem can be written as, by the way, what I've wrote doesn't make sense. Or at least it does make sense, but it's not clear. I should change the variable integration to t, because this x has nothing to do with this x. So I'm integrating with respect to t, the upper bound is x. But x has nothing to do with the variable of integration. What I wrote before makes sense, but it's confusing. So in other words, if you actually think about it, suppose that this is your function f. Then what capital F looks like is that capital F of x, let's say this is A, this is x, is equal to the area from here to here. F of x is this area, right? And then as you change x, you're taking a different area. So suppose, for example, then that's this, let's put it in red, right here is y. Then this would be f of y, right? That's f of x, that's f of y. So this is what this function looks like. And then there's another way to write this theorem, can be written as the derivative d dx of the integral from a to x of f of t dt is equal to f of x. And this is often explained as saying that differentiation and integration are inverse operations. Any questions about that? So one thing to keep in mind is, how is this a function of x? It's a function of x because x is the upper bound of this. Okay, I am not going to prove this theorem, but I'm going to give an incredibly informal proof sketch. Super informal proof sketch. This is completely not a proof. F prime of x is equal to the limits as h goes to 0 of f of x plus h minus f of x divided by h, right? That's the definition of a derivative. Then if we write what this is the limits as h goes to 0 of the integral from a to x plus h of f of x plus h, sorry, f of t dt, minus the integral from a to x of f of t dt divided by h. And that's the area that is the area here, and that area is here. So the difference between these two is the area here. And I can write that as limits as h goes to 0 of the integral from x to x plus h, or I can write it like this, 1 over h, the integral from x to x plus h of f of t dt. Now, when h is small, t is very close to x, right? Because we're just looking at the interval at x to x plus h, and that's a tiny interval. And f of t is approximately constants. It's approximately constant. This is completely not rigorous. This is not a proof. This is not mathematics, but it is an informal sketch of intuition. Then, if this function is constant, then what is the integral? So then it's approximately equal to the integral of a constant function. And that's just going to equal to it's going to be a rectangle. The length of the base is h, right? And the height is constantly f of x. So this is approximately equal to the limits as h goes to 0 of 1 over h times f of x. And that's just clearly f of x because that's constantly equal to f of x. So this isn't a proof, but you can use arguments about continuity to make this rigorous, right? So how much, in other words, if I start increasing the area, how much is the area increasing as I move this along? Well, that's dictated by the height of the rectangles, right? If I add more rectangles in, then their height is going to be dictated by the values of the function at x, right? Any questions about that? Okay, so that was a completely informal proof sketch. You're not going to be tested on this because it's not even a proof. It's very not rigorous, but it's some sketch that might help your intuition as to why this result is true. Okay, let's actually get to using this result for some problems. So here are the problems that come from FTC Part II. Leads to some problems. Well, let's say questions. For example, okay, I should clarify one more thing. First, we have not yet defined what the integral from a to a of f of t dt is. It's specifically, if you look at part 1 of the notes, they assume that the interval has a less than b. But if we're just trying to compute the area over a point, then what should that area be? So in other words, what is the area of this region? Let's say this is A. The region is just a line. What is the area of this line?
F of a minus, or
But there's no width. There's no width. The width is 0. the value. So someone's suggesting the value at the point. But here's the thing. Let's suppose that it was, let's suppose the integral from a to b of f of t dt. Let's say this is a and this is b, is this area, right? As b gets closer to a, this area gets smaller and smaller, right? So when b becomes a, what does the area become? This isn't the derivative. This is just, okay, well, we wrote it right here. It would be h times f of x. But what is h? H is 0 in this case, right? So this is 0. Okay, so that's one convention. Now, what if I consider swapping the indices? So these aren't theorems, these are conventions. What should the relationship between these two things be? In other words, if you calculate area backwards, it actually makes sense to say that the swap sign. With these conventions, we have that the integral from a to b of f of t dt can be written as the integral from a to c of f of t dt plus the integral from c to b of f of t dt. So one way to think about this is if we have a function like this, and this is a, this is b, this is c, then the area from a to c plus the area from c to b is equal to the area from a to b, right? That makes sense. Okay. So this was a preamble. Now let's actually get onto the problems. And you're going to see that these problems aren't difficult. This is the last topic on the midterm. So these type of problems are going to be on the midterm. Suppose that we consider something like f of t, let's call it f of t, is equal to the integral, let's say from some value a. It doesn't matter. Let's say from some, sure. Let's say from the value a for some number a. Sorry, let's call this f of x. From a to x of the function 1 over 1 plus sine squared t dt, right? Then what is f prime of x equal to?
Is it log absolute value of cosine squared at t?
No, we're using the fundamental theorem of calculus part 2. So what does FTC 2 say? That if you have the upper bound, if you have from a to an upper bound and you're differentiating, then it's just the value at the upper bound, right? So f prime of x is equal to what?
So it's equal to the upper bound.
It's equal to the function evaluated at the upper bound.
So 1 plus sine squared x.
Yes, and crucially, has to be in terms of x, right? Not in terms of t. T does not make sense. This has to be in terms of x because t has no meaning in this equation. Okay, now here's the twist. What about the function f of x is equal to the integral from a to x cubed, 1 over 1 plus sine squared t dt. What does f prime of x equal?
It would be 1 over 1 plus sine squared of x to the third.
So, okay, here's our guess. Is that it's 1 over 1 plus sine squared x to the third. So you are right in that we should be evaluating sine at x squared to the third, because that's the point at which the action is happening, right? There should be no other values that are relevant. But here's the catch. How can we write, let's capital C of x equal x cubed. Then what is f of x equal to in terms of f and c? F of x equals to what? In terms of f and c. So remember what the function f does. It is that it takes its argument, it puts it as the upper bound of this integral, right? So if f, the function, takes x, then what does it first do to the number x before putting it as the upper bound?
Gets a derivative?
Not exactly, because what is f of x? What's the difference between f, capital F and little f?
The p-value.
Yeah, the fact that there's an x cubed here. But look, x cubed is the argument to the function, right? So in other words, what f does with the argument before putting it as the upper bound is that it cubes it, right? So f can be written as a composition. What composition is it? It can be written as f of c of x. Does everyone see that? So we have to understand what this function f does. What it does is it takes an argument. So for example, what is f of 5? What does f of 5 equal? Well, it's equal to the integral from a to 5, right? Of 1 over 1 plus sine squared t dt, right? So what the function f does is it takes the argument and it puts it as the upper bound of the function. So what does f do, little f do? It takes the argument, it takes its cube, and then it puts the cube of the function as the upper bound of the function, right? This is the same as f of x cubed. Does everyone see that? If you don't see that, you should ask a question right now. This is very important. Okay, Well, if you see that, then you should be able to tell me what the derivative is. So what's wrong with this derivative? So what is that expression equal to? We can actually write what that expression equals to. So f prime is equal to this, right? So the expression 1 over 1 plus sine squared of x cubed is equal to what? F prime of what?
X cubed.
Yes. Or we could also write that as f prime of c of x. But if little f is equal to f composed c, then little f prime is equal to f prime of c of x. But I also need to do something. What do I need to do? What rule am I applying? I'm differentiating this composition, right? So what rule am I using?
Product rule.
It's a composition. Come on, chain rule, right? Chain rule. And what does chain rule say? The chain rule says that the derivative of f composed c, let's write it without variables of x. F prime is equal to the capital F prime composed with c times the derivative of c prime, right? Or in other words, f prime of x is equal to capital F prime of c of x times c prime of x. So that's what we were forgetting. So the derivative isn't just 1 over 1 plus sine squared of x cubed. I also have a numerator. And what is the numerator? I need to multiply by c prime. What is c? C is x cubed. What's c prime?
Cx squared. Oh, my bad. 2x squared. Or no, 3x squared.
3x squared. Right? Okay, so what is the lesson that we learned? If the bound is not just x, if the bound is a function of x, then you have to do chain rule, right? Okay, now let's instead consider what about, let's say the function g is equal to c composed f. So g of x is equal to the integral from a to x of f of t dt, all cubed. So g prime of x is equal to what? It's just chain rule. Just do chain rule. What do you get? By the way, does anyone have any questions about why this equals this? So this is a type of problem that you're going to see on the exam. So it's very important that we understand this. Does everyone understand why f prime has this 3x squared factor coming in?
Because you're taking into account the chain rule.
Yeah. So in particular, what is little f? Whenever you're differentiating a function, this is what I tell my calc students. The entire secret to differentiating is that you just ask yourself one question. You ask yourself the question, what function am I differentiating? And if you answer that question, then you've differentiated it already. And that sounds like it's a complete platitude that doesn't mean anything, but it actually does mean something. The question of what function am I differentiating is answered by explaining how that function arises from basic functions, right? So remember how in calculus A, what did I mentioned this at the beginning of the class? We know how to differentiate sine, right? That's a basic function. We know what its derivative is, right? We know how to differentiate x to the power of 10. That's a basic function. Now, what happens if you have something like x squared plus sine x to the power of 10? Then how do I differentiate this? What rule do I apply at the top level?
Chain rule.
Chain rule. So what do I get? I drop the exponent down, right? So I write 10. Then I write x squared plus sine x to the power of what?
Nine.
Okay, and I have to multiply this by what?
2x plus, what was this? It's not just cosine, it's sine x times cosine. I'm
No,
sorry, I'm
the
forgetting
derivative
this
of
part.
sine x is cos x, right? We're
Yeah,
just
okay, so
multiplying by
it's
the derivative of
cos x.
this. Okay, right. So what have we done today? So today, I added one basic function to your Calc A toolbox. And that basic function is the function f of x is equal to the integral from a to x of f of t dt. So you know how to differentiate this function. So remember, in calculus A, you just had to ask yourself the question, how is this function built out of basic functions? Well, the twist now is that this function is a basic function. We know what its derivative is. That's given by FTC Part II, right? So now when you look at something like this function right here, you ask yourself, what am I being asked to differentiate? And then you ask yourself, how is what I'm being asked to differentiate built out of basic functions? Now let's look at C. Let's look at F. F is a basic function, right? C is a basic function. If I know how to differentiate F and C, then I know how to differentiate their composition. What is the derivative? I can just write it down in terms of C and F. What does chain rule say? G prime is equal to what?
3.
Oh, okay. Can you say it in terms of C and F first? So it's C prime, what? Of what?
F
Of
of F prime.
f of x. C prime of f of x times what?
F prime of X.
Times, yeah, f prime of x. Okay, now you were about to tell me what it is for this function. Can you, okay, tell me what it is.
3. And then it's F of T.
Which I can write as, well, f of x, right? So a to x of f of t dt.
And then
To the power of?
power of 2. 3, yeah, 2. And
oh, sorry, I should clarify. G is not the function f of t. F of it's one, we actually have a formula for this. 1 over sine squared t, right? So I should write 1 over sine squared t here. Okay, and now what do I multiply by? I multiply by the derivative of this function. And what is that? The derivative of the function on the inside. What is it? So we wrote it here, right? It's just the function, the integrand evaluated as the endpoint, right? So it's 1 over 1 plus sine squared of x, right? Okay, now, any questions about that? So I think that's the idea of how I explained it right here. That's something that really clicks for me. How do you differentiate in Calc A? You have basic functions and then you have rules of composition, right? You just ask yourself, what is my function? How is it built out of basic functions? Well, the only thing that's changed is that this function right here is now a basic function. Does that make sense? Okay, let's make it slightly more interesting. Let's consider the function h of x is equal to the integral from a to the integral from a to x cubed of 1 over 1 plus sine t dt. So that's the upper bound of integration of 1 over 1 plus sine squared t dt. Okay, first off, what is h in terms of f and g? H of x is equal to what? So first off, it's f of something, right? Because I've put something for the upper bound. Does everyone agree? It is f of something, right?
Yeah.
Now, what is the something? We've seen this function before, right? That was the first function, first composition that we considered. We saw that this function right here was f composed c, right? So this is f of c of x, right? Matching my parentheses, I need 3 closing parentheses. So what is h prime of x equal to then in terms of f and c? Chain rule again. It's just chain rule. What do you do? Write down chain rule. I mean, okay, what is this? This is a composition. What's the outer function? F. What's the inner function? F of c, right? So what does chain rule say? It's f prime of what? F of c times what? Times the derivative of the inside function. What's the derivative of the inside function? We already did this.
Was that the C prime times F of no, F of
Well, yeah, it's
yeah.
c prime times something. What's the other thing? I'd like to write that other thing first. You're on the right track.
F of X?
F prime,
F prime
of
of
something.
X.
Of x or of what? It's not of x. F prime of what?
C?
Yeah, of c of x times c prime of x, right? That's the derivative, because remember, that's f composed C prime is equal to F prime composed C times C prime, right? And so F composed C, let's bracket it like this, prime is equal to F prime composed F composed C dots F composed C prime, and that's rewritten as F prime composed F composed C dot F prime composed C dot C prime, right? Okay, well, let's write what this is. So we have, what is F prime? F prime is 1 over 1 plus sine squared. Sine squared of what? Of f of c of x. What is that? That's the integral from a to x cubed of 1 over 1 plus sine squared t dt. So that's f prime of f of c. Then I multiply by f prime of c. So that is 1 over 1 plus sine squared of x cubed. And then I multiply this by c prime, which is 3x squared. So in other words, this big scary function, which had an integral as an upper bound of an integral, it's just chain rule, Michael Spivak writes in his calculus book, it's just chain rule if you keep your cool. So remember, differentiating is easy. You don't have to do clever tricks for differentiating. You just ask yourself the question, what function am I differentiating? And then if you answer how it's built out of basic functions, you just do product and chain rule. Any questions about that? So this is going to be on the exam, and this is on the assignment. This is the last thing that's on the exam. Nothing else that I do today is going to be on the exam. Okay, wait. Sorry, when I say this is the last thing that I do on the exam, we need to do one more example. Let's suppose that f of x, sorry, let's suppose that f of x, or let's say capital F of x, equal to the integral from negative x to x of f of t dt. Then how can I rewrite this? Notice that x is in the lower bound, so FTC 2 does not apply. But I can write this as the integral from negative x to 0 of f of t dt plus the integral from 0 to x of f of t dt. And how can I rewrite the first integral to make this bound up top, go up top? So remember at the beginning, I provided a convention that if you change the order of the bounds, the integral changes by a sign. So I can write this integral right here as the integral from 0 to negative x of f of t dt. Now what happens if I differentiate? So what is the derivative of the first term? Okay, what's the derivative of the second term? Everyone should be able to answer this. What is the derivative of this dx? What have we been talking about for the last hour?
Just f of x.
Yes. Now, what about the derivative of the first term? It's a composition, right? The inner function is negative x. So chain rule is going to give us a sign, right? So what does it become? Well, we can write that it's negative f of negative x times the derivative of negative x, which is -1, right? That's so we get this from chain rule. So overall, we get f of negative x plus f of x. And this makes sense. Why? Because what does this function do? It computes the area. Let's say this is negative x and this is x. So it computes this area. Then how much is this area changing as we change x? Well, it's getting some area based on what f of x is, and it's getting some area based on what f of negative x is. And it should be that both of these terms have a plus because you're gaining area here and you're gaining area here. Any questions about that? So this is the last exam relevance example. If you have a bound at the bottom, or if you have bounds in both places, if you have not constant values, if you have functions of x at the top and the bottom, then you have to split it into two integrals like this. And then if you have something at the bottom, you have to bring it up top. And then you have to do chain rule if it's not just x. So that is the last exam relevant thing. Okay, now I can promise you that we're done for exam relevant things. So FTC Part II is all about solving problems like this. And the main lesson is that this function is now a basic function in your Calc K toolbox, and differentiating is easy, right? We did integration this unit. Integration was hard. Integration was sometimes impossible, and you had to do a lot of tricks. But differentiating, you didn't have to do any of these tricks in Calc K, because differentiating is much easier than integrating. So this isn't hard. This is just differentiating. And you just have to do chain rule. It's just chain rule, right? So, okay, I have one more thing to discuss today, but let's take a 7-minute break because I said that I would do 2 breaks and then I'll do 40 more minutes. So let's do a break until 8:40. 40, right? Sounds good? Okay, see you then. Does anyone have any questions before I move on? Okay, so I am happy to announce that we are 100% done with the theory in this course. We are done with theory. You now know everything there is to know about integration in Calc B. You have a complete Calc B toolbox. There's a question in the chat. Oh, okay. So I privately got a question saying that are there any good resources on this specifically? I will perhaps share some books. I'll send an email about the exam, and then I'll provide some written resources. Although you should probably, I think that's the best way to study would be to go over the examples. I'm going to post these notes here. And oh, if you want video lectures, then well, okay, you can look some things up on YouTube as well. I might send something. I'll look it up. Okay. Let's see. Now, okay. I said that we have a complete Calc B toolbox. So what is the rest of this course going to do? If we're done with the theory, we're now going to be doing what for the rest of the course?
Calculations.
Well, yeah-ish. We've technically been doing calculations in the theory section as well. More specifically, calculations in the interest of what's?
Is it like application of?
Yes, that's the word that I was looking for. And okay, it is doing the thing. It's applications. And what is another word for applications? There is another word for applications.
Word problems?
Exactly. So people said exactly the two words that I wanted to say. It is called applications, but in reality, we are doing word problems. So this course involves a lot of word problems. And that is going to be, this is the 5th lecture, so we are going to have 4 more lectures of word problems. And the first class of word problems, and I don't know, this may sound good to you or it may sound bad, but in Calc A, we had a lot of word problems, so it stands to reason that we would have word problems in here. But the theory is done. So if you, the theory is really the hard stuff, and we did all of the hard stuff at the beginning. This section is more about just setting up problems and pattern matching from examples. So the first type of word problem is area problems. And these are, I guess, more not exactly word problems, like there's a lantern moving at something. It's asking you to find the area between 2 functions. So it's a half word problem, but it's an application. Yes. So what is an example of an area problem? Well, let's suppose that we have some A and some B. And suppose that we have some function f and we have some function g. Well, here's a very simple example. What is the area between f and g? What is this area? So an example question is, computes the shaded area. And towards this, there's one result that we use. And this results, okay, I should say this. So at the beginning of this course, we motivated the notion of area. We said that integrals were a type of area. But more specifically, it was known as the area blank. What is blank? The area. So I called it where definite integrals were the area under the curve, were a computation of the area under the curve. So those regions looked like this. So I can draw it maybe as something like this. And this region is not of that form. But here's the catch. There's something known as Cavalieri's theorem. And this is a historically significant result in the development of calculus. So this is historically significant in the early development of calculus. And what the theorem says is that suppose I have some region. Let's consider a region like a triangle. And then this region has cross sections. Now, suppose that I have any other region that's lined up with this region. But it looks different. Let's say this edge looks like something pretty groovy like this. But then let's say I take these cross sections and I move them over here. And then I form a region like this. And the property that these regions have, that's going to erase. So these cross sections coincide. In other words, they're the same length. Then what should be true about these two areas? Have the same length. Then what? The areas are what?
Would that make them equal?
Yeah. So this results is in the early developments of calculus, people postulated it, and then they didn't have an adequate way to make it formal or an adequate way to prove it. And we're not going to be able to prove it either because we do not have a general notion of area. We do not have a general notion of area. So we can't prove this. And an example of a general notion of area, in higher math classes, in like fourth year math classes, you have a notion such as the Lebesgue measure. So you don't know what this is, but there do exist general notions of area. And when you have a way to define the area of all regions, not just areas under the curve, then you can prove this results. But we're going to take this as an assumption. And one reason that it's reasonable is that suppose an area is consists of summing up some slabs of some finite thickness. So suppose we approximate this with rectangles. Suppose we make these have some thickness. Then the area consists of the areas of these slabs. And if these slabs are just rectangles, then moving around those rectangles doesn't change the area at all, right? And the area, as we've conceived it, is really a limit of these rectangles as the height goes to 0. So this makes sense. If they were finite slabs, then you could move one slab over the other and it wouldn't change the area because the area is just this area that you see. They're not covering each other up. They can move freely. So that's why this is true. Well, what does this say about computing areas between two functions? So suppose that we have here f, and suppose here that we have g. And suppose that f is greater than or equal to g on the interval AB. So this is my A, and this is my B. Then this region I can draw as cross sections. So suppose I take some point X and I take the cross section over X. Then what is this height? What point is this? This is the point X comma what? Well, this is the function f, right? So it's x comma f of x. And what about the point at the bottom? That's the point x comma what?
G, so
Yep.
G of x.
Okay. Now, what is the height of that slab? Of the slab at x? Is what? What's the length of this red line segments? Someone?
Is it f of x minus g of x?
Exactly. So by Cavalieri's theorem, let's suppose that instead of this, I consider the function f minus g. So suppose I take all of these slabs and suppose that I shift them down. And then I just consider the function here. It looks like this is getting thicker. And suppose this is the function f minus g. Then what is this area? How can I express this area? Oh, also my headphones are dying, so I can't hear what people are saying. Okay, how do I express this area in terms of an integral? So this is the area under the curve of the function f minus g, and it's from a to b.
So
So how do I write that area?
integral of f.
What are the bounds?
Integral from a to b of f, and then minus g, the integral of, yeah.
Yeah. So this is the area under the curve. Okay, let me quickly expand this page. So according to Cavalieri's theorem, this should measure the area. This should be the area between the regions. So in other words, if f is greater than or equal to g on the interval a comma b, then the area between f and g over this interval is the integral from a to b of f of x minus g of x dx. And the reason that this is true is because of this Cavalieri theorem, that I'm able to move all of these slices down, and then all of the heights are just f of x minus g of x. So that should be intuitively appealing, right? Integrals compute areas under the curve, but by Cavalieri's theorem, we can translate an area between two functions to an area under the curve just by subtracting one function from the other. So let's give an example of a word problem that arises from this. So this is going to be an interesting word problem. I'm going to ask for this. Find the area of the region or, by the way, are there any questions about this? Okay, so here is an example. Find the area of the region bounded by the curves f of x equals x cubed minus 3. Sorry, x cubed minus x, and g of x is equal to x squared. Okay, so here I should add some color example. So what is going on? I haven't given bounds. And I can explain what's going on by drawing a graph, although drawing a graph doesn't have to be a part of your solution, but drawing a graph will explain what's going on. So first off, the function x cubed minus x looks like this. And the function x squared looks like, well, the usual parabola. I'm not happy with the second hand. Is it going to erase everything? Okay, it's not going to erase everything. Okay, that's okay. And the function x squared looks like this. So if I were to draw the area fully enclosed by those curves, what would that area look like? Well, okay, I'll draw it. So the area fully enclosed by those curves is the area that I'm about to shade in red. Now we're not including, we are not including the infinite unbounded areas. The infinite unbounded areas to the sides. So I want a sum of these two areas. And in other words, I need to find bounds first. So first I want to find what these bounds are. Is it, by the way, clear what from the picture, what the area that I want is? Okay, so now we solve for the points of intersection. Bounds of integration. And so I look at my equations. They are x cubed minus x and x squared. So I set them equal. And what does that imply? That implies that x cubed minus x squared minus x is equal to 0. Now, I can obviously factor an x out of all of this, right? And so what are the roots?
Zero and plus or minus 1.
0 is a root, plus or minus 1 are not roots. You actually have to use the quadratic formula for this. So sing the song. What does the song say?
Negative b plus minus the square root of b squared minus 4ac all over 2a.
Good, that is the song. So b here is -1, so negative b is 1, plus or minus the square root, b squared, -1 squared is 1, minus 4ac. A is 1, c is -1. So ac is -1, and minus 4ac is plus 4. So in other words, I can just rewrite this as the square root of 5 over 2, right? So, okay, now, so if I go back to my graph, I can label this. This point right here is the negative roots, 1 minus square root 5. Square root 5 is bigger than 1. This point right here is, of course, 0. And this point right here is 1 plus the square root of 5 over 2. Now, here's the thing. It's clear. So I have two intervals. The intervals one minus square root 5 over 2 to 0 and 0 to 1 plus square root of 5 over 2. Now I want to know which of f or g is bigger on each interval. Now, from the graph, it's clear which one is bigger, right? So the green one was g of x, and the blue one was f. So if I have this graph provided to me, then I know that f is bigger on the first interval and g is bigger on the second interval, right? But the thing is, if you have two functions, then producing the graph is hard. and more specifically, how can you be sure that you've produced the correct graph? So here I've given you the graph, and so you know, but in general, you don't know which one is bigger. And so there's a very robust method for finding which one is bigger. And can anyone guess what that method is? So one thing to note is that f and g only intersect at these 3 points, right? So at every single point in between, one of them is bigger than the other, and that doesn't change across this interval because they don't have any intersection points and they're continuous functions. So I can just check whether one of the functions is bigger than the other function at some point in the interval. And how do I do that? So I can do that just by plugging in values, right? Does that make sense? So what I need is I need some number between these two numbers. If I choose either of the endpoints, then the functions are going to be equal because that's what the endpoints are after all. They're the points of intersection of the function. So I can look at, for example, 1 minus square root 5 over 2, and that's less than 1 minus square root of 4 over 2 because I'm subtracting a smaller number. And that's equal to minus 1/2, right? So the number minus 1/2 is in this interval. So I'm going to evaluate both functions at negative 1/2. Sorry, negative 1/2. And g of negative 1/2. Now, also, we know, okay, let's just do the negative 1/2 point first. So f is x cubed minus x, and g is x squared. I'll write that down here. Okay, so f of this is, well, it's minus 1/2 cubed, so that's going to be minus 1/8. And then minus x, so minus 1/2 is plus 1/2. And this I can rewrite as, well, I can rewrite this as minus 1/8 plus 4 over 8, which gives me 3 over 8, right? Now, what about g of minus 1/2? Well, it's minus 1/2 squared. And that's 1/4. And that's equal to 2/8. So which one is bigger?
The f.
Yes, thus f is greater than or equal to g on the entirety of this first interval because they have no intersection points. Now, they intersect at the point 0, but we don't necessarily know that they cross. They could intersect and that they could go their respective ways, right? So we could have a situation that looks like this. These have an intersection point. Let's say that this is the intersection point, but they go their separate ways. So we also need to know which one is, well, 0 is less than 1 is less than 1 plus square root 5 over 2, because square root 5 is bigger than 1. So this number is bigger than 1. So I can plug in f of 1 and g of 1. And these are easy. So f of 1 is 1 cubed minus 1. That's 0. and G is 1 squared is 1. So G is greater than or equal to F on the interval 0 to 1 plus square root of 5 over 2. Now we combine both of these facts to write down what the area is. Thus, the area is given by, and so I'm writing this problem up the way that I'd like you to write this problem up. So the area is given by A. We can write a area is equal to the integral from 1 minus square root of 5 over 2 to 0 of what expression? F minus G or G minus F?
G minus F.
Well, F is bigger than G on this interval, right?
Oh, okay.
So we subtract the smaller from the bigger. Plus the integral from 0 to 1 plus square root of 5 over 2. Now G is bigger than F. So we do not want a signed area. Areas under the curves are signed area. We want actually area to be a positive number. So I want the sum of the area of this region as a positive number plus the sum of the area of this region as a positive number. And that's why I need to know which one is bigger. Because remember, in Cavalieri's theorem, in this definition of area, we had the assumption that F was bigger than G on the interval that we were doing this. And here there are two intervals and one function is bigger than the other on each of them. So we need to split it into two different integrals. Okay. Well, then I can just write what these functions are and find what the antiderivative is. So F is x cubed minus x, and G is x squared. And this one is the other way around. So it's x squared minus x cubed minus x. Then I can write down what the antiderivative is. So what's the antiderivative? It's just a polynomial. Are we all so sleepy that we can't integrate a polynomial? Come on.
X to the 4th over 4 minus x squared over 2 minus x cubed over 3.
Yeah. And so this is the antiderivative, and now we put the bounds here. And then the other one, it just differs by a sign. So I'm not going to make someone say that again. I'll just write it here. So x cubed minus 3 minus x to the 4th over 4. And then this is plus x squared over 2. And then I put the bounds here, 0 to 1 plus square root of 5 over 2. And now, yes, now you evaluate this. And this example is sort of bad. In this example, it's ugly. Well, the answer comes down to a good answer at the end. It's not very nice. So I would ask you a better example. But this example is very good because of solving for the areas. So it turns out that the area does not come to a number, a nice number. It has radicals. But this is an excellent example for solving for the intersection points and finding which one was bigger. So you actually, to finish this example, you have to compute what these numbers are. But it's yeah, on the exam, you'll actually have situations where it's less ugly as to what the actual final area is. But in principle, you could just write down the expression. You can just write it down, and that would give you the area of this region. So I don't think I'm going to do another example today. I think this last example was pretty relaxed. So we're now doing the applications part of the class. There's a lot of time until the end of the semester. And we're done with the theory. So some of you are happy to hear that. The midterm is precisely going to be on all of the theory, except for the fact that I won't have any questions it's going to cover the same material as the assignments. And on assignment 3, I don't actually have anything with definite integrals where you change the bounds. So I won't have this bound changing on the exam. This might actually be bad news because we saw that bound changing was actually easier for integration by substitution, because you didn't have to substitute back. But because it's not on the assignment, I'm not going to put it on the exam. So that'll be on some subsequent homework problems. Also, I made this homework. I didn't put any super tricky integrals on this homework. There are a lot of problems that I could have put that I didn't put. So the way this is going to work is that the remaining 2 assignments are going to have applications on them, but then I'm also going to put some integration problems on them. And the integration problems are going to be more tricky problems, but they're not going to use any new techniques. So they're going to use all of the old techniques, and then they're going to be so that you don't get rusty on it, and so that you can improve your integration skills, because they need to be good for the final. Sounds good?
So you said the midterm was good. Obviously, it's going to be everything we've done up to FTC 2, but
Yes.
you say it was going to be more theory-based?
Oh, well, what I mean by theory-based is that it does not cover the applications part that I did. The questions on the exam are going to be very similar to assignment questions.
Oh, okay.
So I just call the first half of the class up to the application section, the theory section. Like computing integrals and knowing all of these tricks, that's sort of theory. It's computation, but the computation has a theory behind it. You need to learn how to do integration by parts and how to do integration by substitution. And so that is the learning stuff, not the applying and solving word problems section, which is a bit tedious, to be honest. I'll send an email with some more information about the midterm. But there isn't that much more to say other than the fact that it's going to be a bit shorter than an assignment, which if the problems were problems that you hadn't seen before, it would be a bit cruel to ask you to solve them in a day because you usually have a week. But they're the problems that you've seen before. So the point is that I will post the solution to homework 2 as well, but I won't post the solution to homework 3 because it's not due before the exam. But the questions on the 3rd homework are part of the exam material.
Are all of them on the 3rd assignment a part of the exam material?
Yes.
Okay.
So the only thing that we've done in the theory section that's not on the exam is the way that bounds change for definite integrals. And that's only because I didn't put any assignment questions for it. But I will tell you right now, and I've told you this last time, there will be a question on computing Riemann sums, computing an integral using Riemann sums. There are now 3 problems written up fully, 1 in the notes and 2 problems on the solutions. By the way, I'll update the first notes because we changed the definition of the definition of integration in the notes isn't the one that we're using. We're taking a limit over partitions, not doing this neighborhood and finding something that fits. So I actually have new versions of those notes. I just need to upload them. That takes a second. I had this for a week. I don't know why I haven't done it yet. Executive functioning things, they're hard. And I'll also upload all of the PDFs of these notes.
Are you going to be uploading solutions for homework too? Sorry, I know it might be a lot.
Yeah, I mentioned that. I will be. Yeah.
Okay, thank you.
I'll
Sorry,
do
I
that
just wanted
soon.
to clarify.
So that's going to be done, I say, by tomorrow. It's not going to be probably easier for me to write this up than the solutions in the first homework. the first homework you have to be detailed, but at the same time, there are 14 integrals on this, so I don't know. It should be uploaded by the end of tomorrow.
You said,
I'll promise you by the end of tomorrow. You can hold me up on that.
Thank you.
you
Okay.
said you were gonna change the settings on the Blackboard assignment thing.
Oh, thank you for reminding me. Good. Thanks. Okay, I will do that as well. Anything else? Okay, see you on next Tuesday. That'll be after the exam. And then some of you may want to contact me for office hours prior to then. So I am available for office hours. Just send me an email. I've been meeting with plenty of students fairly frequently. Okay, see you on Tuesday. Good luck on the midterm.
Thank you so much.
Okay, see you.